Find somewhere comfortable. You don't need to sit up straight or keep your eyes open. You don't need to hold on to any of this. The words will come and they will pass, and that is perfectly fine. If you drift somewhere along the way, that's not a failure. That's the whole point. We are in no hurry tonight. The dark is patient, the night is long and quiet, and we have all of it. Tonight we're going to wander through one of the most quietly beautiful ideas in all of science. Not loudly, not urgently. Just as a kind of slow, unhurried exploration, the sort of thing you might turn over in your mind while watching rain move across a window. The idea is this: no two electrons in the universe can ever be in exactly the same state at the same time. Not in your body, not in the stars, not anywhere, ever, in the whole of space. And that single rule, that one strange, deep, unbreakable rule, is the reason matter has shape. It is the reason atoms hold together. It is the reason you are solid, and the chair or the bed beneath you is solid, and the world has the texture and structure it does, rather than collapsing into a featureless, dimensionless nothing. We'll move through this slowly. 8 chapters, each one a little deeper than the last. You don't need to follow every word. You don't need to remember anything. Just let the ideas settle around you, the way the night does. Whenever you're ready, we begin. There is something almost magical about the light that comes through a prism. You've probably seen it, a narrow beam of white light entering one face of a triangular piece of glass and emerging on the other side, spread into a fan of color, red bleeding into orange, orange into yellow, yellow into green, and on through blue and into the deep violet at the far edge. It is one of those sights that feels both familiar and quietly astonishing, the kind of thing that stops you for a moment even when you've seen it many times before. But here is the thing that physicists in the early 20th century understood, and that most people walking past a prism in a shop window do not. The light coming from a hot gas is not a smooth rainbow. It is a collection of precise, specific lines. Hydrogen, when it is heated until it glows, produces 4 visible lines, 1 red, 1 blue, green, 1 blue, and 1 violet. Always those 4. Always in exactly those positions. Why not every color? Why only those 4? What was it about a hydrogen atom that allowed it to emit light only at those precise wavelengths, as if it were choosing from a menu rather than producing a continuous stream? The answer, when it came, was extraordinary. It turned out that the electron in a hydrogen atom cannot exist at just any energy. It is confined to specific energy levels, like rungs on a ladder, with gaps between them where no electron can rest. When the electron drops from a higher rung to a lower one, it releases that energy as a photon, a particle of light. And because the energy gaps between the rungs are fixed and specific, the light produced has fixed and specific wavelengths. They are the atom's fingerprint. Niels Bohr worked this out in 1913, building on ideas from Max Planck and Albert Einstein. His model of the hydrogen atom was, for its time, a triumph. He imagined the electron orbiting the nucleus in one of a set of allowed circular paths. The analogy to planets orbiting a star was irresistible, even if ultimately misleading, and he showed that his model predicted exactly the wavelengths of light that hydrogen was observed to produce. The agreement was precise. The scientific community was impressed. Bohr was celebrated. And then someone tried to apply the same model to helium. Helium has 2 electrons instead of 1, 2 particles orbiting the nucleus instead of 1. It seems like a modest addition. Surely the model would extend naturally with a little adjustment. But it didn't. The mathematics became intractable. The predicted spectral lines didn't match the observed ones. Something was wrong, or rather, something was missing, something that the 2-electron case demanded, but that the 1-electron case had not required. The problem was not just helium. Move further along the periodic table and the failures multiplied. Lithium has 3 electrons. Beryllium has 4. Carbon has 6. And for each of these elements, the spectral lines told a story that the existing models couldn't fully read. There were too many lines, or lines in the wrong places, or patterns of splitting and doubling that had no clean explanation. The atom, it seemed, was keeping a secret. One particular puzzle was the way spectral lines behaved when a magnetic field was applied. In some atoms, a single spectral line would split into 2 very close lines, a phenomenon called anomalous splitting, because it refused to fit neatly into the existing framework. The word anomalous in science is interesting. It means we see it, we can measure it, and we have no idea why it's happening. Anomalous splitting was one of those irritating facts that accumulated in the notebooks of physicists without resolution. There was also the matter of the periodic table itself. Why does the first row of elements stop at 2, hydrogen and helium? Why does the second row contain exactly 8, lithium through neon? Why do the patterns repeat in the way they do? Bohr had proposed the idea of electron shells, each capable of holding a certain number of electrons before the next one began to fill, but the question of why each shell held the number it did remained unanswered. The rule was observed. Into this atmosphere of accumulated puzzlement arrived Wolfgang Pauli. He was 24 years old in 1924 when he turned his full attention to the problem of atomic spectra. He had been a prodigy from his earliest years. He published his first scientific paper at 18, a paper on the theory of general relativity that was good enough to be read seriously by the community. His doctoral supervisor was Arnold Sommerfeld, one of the great teachers of theoretical physics, and Sommerfeld recognized immediately that his student was something unusual. Not just clever, not just hard-working, but possessed of a kind of intellectual ruthlessness, a refusal to accept a half answer, a restlessness in the presence of anything that didn't quite fit. His colleagues felt this. He had a reputation for directness that could shade into severity. He would listen to a presentation and then, without warmth, identify the precise point at which the argument had gone wrong. His letters were full of phrases like completely wrong and not even wrong, the latter meaning that an idea was so poorly formed it couldn't even be evaluated as right or incorrect. He was not unkind exactly. He simply could not pretend to be satisfied when he wasn't. And he was not satisfied with the state of atomic physics in 1924. Something was missing, and he was going to find it. He spent months working through the spectroscopic data, the catalogues of spectral lines, the patterns of splitting, the anomalies that everyone had noted and no one had explained. He became convinced that the answer lay not in some new force or some new geometry of orbits, but in a new property of the electron itself, something that no one had yet named or measured, something that could take only 2 values. He called it, in German, Zweideutigkeit, two-valuedness. He didn't know what it was physically. He couldn't picture it. But the mathematics demanded it, and the data confirmed it, and for Pauli, that was enough to begin. By early 1925, he had formulated the rule that would bear his name. No 2 electrons in an atom, he said, could share the same complete set of quantum properties, whatever those properties were, and the physical meaning of the 4th one was still unclear. Each electron had to be, in some sense, uniquely itself. Unique in its quantum address. And that uniqueness, that enforced individuality, was what gave the periodic table its structure, what explained the spectral lines, what told the electrons where they could and could not go. It was a rule that came before its full explanation. The explanation would follow from other hands in the months and years ahead, but the rule itself was there, clear and complete. waiting for the world to understand what it was saying. Picture a theatre, not a small one, an immense one, vast and ancient, with hundreds of levels rising into the dark above you and spreading outward in all directions. Each seat in this theatre has an address, and the address has 4 parts. The first part is the floor. Which level of the building are you on? The ground floor is the lowest, the most intimate, the closest to the stage. The higher you go, the more seats there are, and the more distant the view. In an atom, this first number, physicists call it the principal quantum number, describes the energy shell the electron occupies. The first shell is the lowest energy, the closest to the nucleus. These shells are numbered beginning at 1, and in principle they extend as far as the atom has electrons to fill them. The second part of the address is the section of the floor. Each level of the theatre is divided into sections of different shapes. On the ground floor, there is only one section, and it is spherical, a round, enclosed space like a bubble. On the second floor, there are 2 sections, one spherical and one shaped like a pair of lobes, like a figure 8 or a dumbbell extending outward in space. On the third floor, there are 3 sections, the sphere, the dumbbell shape, and a more elaborate arrangement of lobes and rings. These sections correspond to what physicists call subshells, and they are labeled with letters S for the sphere, P for the dumbbell, D for the more complex shapes, and F for the most intricate of all. The shape matters because it describes how the electron's presence is distributed in space. An electron in an S subshell is equally likely to be found in any direction from the nucleus. Its presence wraps around the center in a smooth spherical cloud. An electron in a P subshell is concentrated along a particular axis, forming those characteristic lobes on either side of the nucleus. The shape of the orbital is not just a geometric curiosity. It determines how one atom bonds to another, how molecules form, how chemistry happens. The third part of the address is the orientation of the section. In a theatre with multiple sections on each floor, each section might face in a different direction. A dumbbell-shaped orbital, for instance, can point along 3 different axes in space, up and down, left and right, in and out. These 3 orientations are each a distinct seat. The number of orientations available depends on the shape of the subshell. The spherical S subshell has only 1 orientation. The dumbbell-shaped P subshell has 3. The D subshell has 5. The F subshell has 7. This third quantum number, the magnetic quantum number, specifies which orientation the electron occupies. So far, the address has 3 parts: the floor, the section, and the orientation. And if you count up all the distinct seats defined by those 3 numbers, you find that the first floor has 1 seat, the second floor has 4, the third has 9, the fourth has 16. The pattern is 1, 4, 9, 16, the squares of the floor numbers. But here is where Pauli's insight enters. Each of those seats can hold not 1 electron, but 2. And the reason is the 4th part of the address. The 4th quantum number describes a property of the electron that has no analogy in ordinary experience. It is called spin, and it is important to say clearly what spin is not before saying what it is. Spin is not the electron rotating on its axis the way a planet rotates. When physicists first named it in 1925, the image of a spinning ball was tempting, and 2 young Dutch physicists, Samuel Goudsmit and George Uhlenbeck, proposed exactly that picture when they identified spin as a real, measurable property of the electron. But the picture breaks down very quickly. If you try to calculate how fast the electron's surface would have to be moving to produce the observed magnetic effect, you get a speed greater than the speed of light, which is impossible. It is something intrinsic to the electron, a form of angular momentum, which is the physics term for the quantity associated with rotation, but one that exists in the electron without any actual spinning. It is a purely quantum mechanical property. It simply is what it is. What matters for our purposes is that spin can take only two values. Physicists call them spin up and spin down, though those words imply a direction that is only meaningful when you put the electron in a magnetic field. You can think of them as two states of being, two modes that the electron can inhabit, like a light switch that can be on or off and nothing in between. Goudsmit and Uhlenbeck published their identification of spin in 1925, the same year Pauli published his exclusion principle. The two discoveries fitted together immediately. Pauli had known a fourth, two-valued property was needed. Goudsmit and Uhlenbeck had found it. And now the counting works out beautifully. Each seat in the theatre, defined by the floor, the section, and the orientation, can hold two electrons, one spin up and one spin down. So the total number of electrons that can fit on the first floor is 2, one seat. The total on the second floor is 8, 4 seats, 2 spins each. The third floor holds 18, the fourth holds 32. 2, 8, 18, 32, twice the squares of the floor numbers. The formula is 2 times n squared, where n is the floor number. And look at the periodic table. The first row contains 2 elements, hydrogen with 1 electron and helium with 2. The second row contains 8, lithium through neon. The third row contains 8 elements in its main block. The formula, falling out of the geometry of quantum addresses and the exclusion principle, matches the structure of the periodic table with exact precision. This is not a coincidence. This is the mechanism. The periodic table is the shape. It is because electrons fill these quantum addresses one by one, and no two electrons can share an identical address. Spin itself, even though it cannot be pictured as a tiny ball spinning, is entirely real and measurable. A spinning charge creates a magnetic field, and even though the electron isn't literally spinning, its spin produces a magnetic moment, a tiny magnet-like property that can be detected. Iron atoms, with their particular arrangement of electrons and their unpaired spins pointing in the same direction, create the familiar magnetic pull that holds notes to your refrigerator. The theatre image can be allowed to fade now. What it leaves behind is the essential shape of the idea, 4 coordinates, 4 numbers, 4 parts of a quantum address. And the rule, simple, absolute, without exception, that no 2 electrons in the same atom can share all 4. Every electron holds its place uniquely. Every seat in the quantum theatre is occupied by at most 1 electron with each spin value, and from that single constraint, the entire architecture of matter begins to emerge. There is a deeper question hiding inside the exclusion principle, and it is one worth sitting with for a moment. The rule tells us what cannot happen, but it doesn't, on the surface, tell us why. Why should electrons be forbidden from sharing a quantum state? What is it about the nature of electrons, about the nature of matter itself at its most fundamental level, that makes this impossible? The answer comes from something stranger and more beautiful than the rule itself. Consider 2 electrons. In ordinary life, we are used to the idea that 2 objects can be identical in every measurable way. 2 coins minted from the same die, 2 grains of sand from the same beach, and yet still be distinct things because they occupy different positions in space, and we can, in principle, keep track of which is which. If you pick up one coin and put it down again, you know it's the same coin. It has a continuous history. It has, in a sense, an identity. Electrons do not work this way. 2 electrons are not merely similar, they are not nearly identical. They are, in the fullest possible sense, absolutely indistinguishable from one another. There is no property, no color, no texture, no internal structure, no history that could ever tell one electron from another. If you have 2 electrons and you swap them, The universe does not change in any way that could, even in principle, be detected. They are not two things that happen to be the same. They are, in some deep sense, instances of the same thing. This indistinguishability is not a limitation of our instruments. It is not that we simply lack the technology to tell them apart. It is a fundamental feature of quantum reality. Electrons are truly, irreducibly identical. Now, in quantum mechanics, the state of a physical system is described by a mathematical object called a wave function. The wave function, and this is the key idea, encodes everything that can be known about a system. It is not a physical wave in any ordinary sense. It is a mathematical description, a probability landscape that tells you where particles are likely to be found and how they are likely to behave. When you want to describe two electrons together, you write a wave function for the combined system. Here is where the indistinguishability becomes crucial. If two electrons are truly indistinguishable, then swapping them, mathematically exchanging their positions and all their properties, cannot produce a physically different situation. The wave function before the swap and the wave function after the swap must describe the same physical reality. But there are two ways a wave function can satisfy this requirement. It can remain completely unchanged when you swap the two particles. Or it can change sign, flip from positive to negative or negative to positive, while still describing the same physical probabilities, because in quantum mechanics, the observable quantities depend on the square of the wave function, not on the wave function itself. A positive number and its negative have the same square. So there are two possible types of wave function for identical particles, those that stay the same under a swap and those that change sign under a swap. Physicists call the first type symmetric and the second type antisymmetric. And here is the extraordinary fact. Nature makes a clean division. Every type of particle in the universe falls into exactly one of these two categories, and which category it falls into is determined by its spin. Particles with half-integer spin, 1/2, 3/2, 5/2, have antisymmetric wave functions. They are called fermions after the physicist Enrico Fermi. Particles with integer spin, 0, 1, 2, have symmetric wave functions. They are called bosons after Satyendra Nath Bose. Electrons with their spin of 1/2 are fermions. Photons, the particles of light with their spin of 1, are bosons. Now comes the step that makes the exclusion principle not just a rule, but an inevitability. Suppose you try to place two fermions, two electrons, into exactly the same quantum state, same shell, same subshell, same orientation, same spin. Everything identical. What happens to the wave function? When you swap the two electrons, since they are in identical states, nothing about the physical description changes. The wave function must be the same after the swap as before, but the wave function is antisymmetric. It must change sign under a swap. The only way a number can equal its own negative is if it is 0. The wave function is 0. A zero wave function means a zero probability of finding the system in that configuration, not a small probability, not a vanishingly small probability. 0. The configuration does not exist. It cannot exist. The mathematics of antisymmetry makes it impossible. This is why the exclusion principle is true. It is not an additional law imposed on top of quantum mechanics from outside. It falls directly out of the antisymmetry of the fermion wave function, which in turn falls directly out of the indistinguishability of identical particles and their half-integer spin. The whole chain is logically airtight. Paul Dirac worked this out formally in 1926, synthesizing the behavior of fermions and bosons into a coherent mathematical framework, what Pauli had discovered empirically, a rule that the data demanded. Dirac showed to be a mathematical necessity. The rule and the reason snapped together like two pieces of the same thing. Now consider what happens for bosons. Their wave functions are symmetric. They stay the same under a swap. There is no zero wave function constraint. Any number of identical bosons can occupy the same quantum state simultaneously. There is no exclusion, no limit, no rule forbidding them from piling in together. The consequences of this are visible. Laser light is the most vivid example. In an ordinary light source, a candle, a lamp, photons are produced with random phases, random directions, random wavelengths. They are a crowd moving in all directions at once. But in a laser, enormous numbers of photons are coaxed into the same quantum state, the same wavelength, the same direction of travel, the same phase. They move together as a single coherent river. This is possible precisely because photons are bosons. There is nothing preventing them from occupying the same state, and with the right arrangement of mirrors and an active medium, they do exactly that. You could not make a laser from electrons. You cannot concentrate electrons into a single shared state. They resist it, fundamentally and without exception, because of what they are. There is something almost philosophical in the contrast. Bosons are, in a sense, gregarious. They prefer to be together, and the more that pile into a state, the more likely additional ones are to join. Fermions are solitary. Each one insists on its own unique address. And it is that insistence, that quantum stubbornness, that gives matter its structure, its volume, its resistance, its reality. The wave function changes sign. The configuration becomes zero. The electron cannot be there. From those three steps, everything follows. Imagine a building under construction. The ground floor goes up first. It is small, just one room, capable of holding 2 occupants. The builders fill it before they move upward. Then the second floor, larger, with 4 rooms and space for 8. Then the third, larger still. Each story fills before the next begins, and the character of the building, what it looks like from the outside, what it can be used for, depends entirely on how many occupants are present and which rooms they're in. This is, in essence, how atoms are assembled as you move along the periodic table. Hydrogen is the simplest. 1 proton in the nucleus, 1 electron in the lowest available room, the first shell, the spherical S subshell, spin up. That's the whole atom. 1 electron, 1 quantum address. The spectral lines of hydrogen are the fingerprint of that single electron jumping between the available energy levels, and they are beautifully simple. A handful of precise lines, clean and well separated, exactly as Bohr's model predicted. Helium adds 1 more proton to the nucleus and 1 more electron. The second electron settles into the same room as the first, same shell, same subshell, same orientation, but with the opposite spin. Spin down. The 2 electrons fit together perfectly, 1 spin up and 1 spin down, and the first shell is now completely full. Helium's ground floor is occupied, both seats are taken. And this has a consequence that is immediately visible in helium's chemistry, or rather, in its complete absence of chemistry. Helium does not bond with anything. It does not form molecules. It drifts through the world as single atoms, entirely aloof, interacting with almost nothing. The reason is that its electron shell is full. To form a chemical bond, an atom needs to be able to share or exchange electrons with another atom, to offer a vacant seat or to reach toward one. Helium has no vacant seats and no desire to give up the ones it has. It is chemically inert, complete, self-contained. Lithium arrives next, with 3 protons and 3 electrons. The first 2 electrons fill the ground floor exactly as in helium. The third electron has nowhere to go but the second floor. It settles into the second shell's S subshell, the lowest available room on that level, sitting alone, unpaired, with no companion sharing its orbital. This single, outermost electron is lithium's entire chemical personality. It is loosely held, The second floor is further from the nucleus, so the pull of the positive nucleus on this electron is weaker, and it is easily given away. Lithium is reactive. It donates that electron readily to other atoms. It forms compounds without hesitation. The difference between helium's serene inertness and lithium's eager reactivity comes down to a single electron and which floor it occupies. Moving along the second row, electrons continue to fill the available rooms on the second floor. Beryllium fills the second shell S subshell with 2 electrons, pairing them up. Then comes boron, and the P subshell begins to fill. The P subshell has 3 orientations, 3 rooms, each capable of holding 2 electrons. Boron puts 1 electron in the first of these rooms. Carbon puts 1 in each of the first 2. Nitrogen puts 1 in each of all 3. Nitrogen's 3 half-filled P rooms are particularly interesting. The electrons in them are unpaired. Each room has 1 occupant, not 2. This gives nitrogen a moderate reactivity, and its 3 available bonding sites make it the cornerstone of amino acids and proteins. But it is carbon, at element 6, that deserves the most careful attention. Carbon has 4 electrons in its outer shell, 2 in the S subshell and 2 in the P subshell, with 2 more P rooms still available. This gives it 4 partially filled outer states, 4 positions where it can share electrons with other atoms, 4 potential bonds. And the geometry of those bonds, the angles at which the p orbitals point in space, the way the s and p orbitals blend together into hybrid shapes, gives carbon a uniquely versatile bonding geometry. It can form chains. It can connect to hydrogen, to oxygen, to nitrogen, to itself. The result is an almost unlimited variety of molecular structures, and those structures are the foundation of organic chemistry, which is to say, the chemistry of living things. Every protein in your body is a carbon chain, every strand of DNA, every lipid membrane surrounding every cell. The reason life is built from carbon rather than from any of the other elements is ultimately traceable to carbon's quantum address, to the specific arrangement of its 6 electrons across the available orbital rooms, 4 of them poised and ready to bond, giving the atom a flexibility that no other common element can match. Continuing along the second row, oxygen fills its outer shell further, leaving 2 of its p rooms with unpaired electrons, which is why water, with its 2 hydrogen atoms bonding to those 2 sites, forms the particular angled shape it does, with its remarkable properties of surface tension and solvent power. Fluorine has 1 vacancy left, and is extremely eager to fill it, making it among the most reactive of all elements. And then neon, with its second floor entirely occupied, both the S and all 3 p rooms filled, 8 electrons completing the shell, is as inert as helium, chemically silent. Satisfied. Satisfied. The third row begins again with sodium, which sits in precisely the same structural position as lithium, 1 lonely electron on a new floor, loosely held, easily given away. Sodium and lithium behave similarly in chemistry, and this is why they appear in the same column of the periodic table. The periodic table is not arranged arbitrarily. It is arranged by electron configuration. Elements in the same column have the same number of outer electrons in the same type of orbital, and therefore the same fundamental chemical character. As the rows extend further, the D subshells begin to fill. These are the transition metals, iron, copper, nickel, gold, with their more complex electron arrangements and their rich variety of chemical behaviors. The d orbitals have 5 rooms, each holding 2 electrons, contributing 10 elements to each transition row. Further along, the F subshells begin, with their 7 rooms and 14 elements. The lanthanides and actinides, the long blocks at the bottom of the periodic table that are often shown detached from the main body simply for reasons of space. Iron is worth pausing on. Its outer d subshell contains 5 electrons with parallel spins. the same spin direction, because electrons in different rooms of the same subshell prefer to be spin up rather than doubling up. This arrangement of 5 aligned spins gives iron its magnetic properties. Those aligned spins, each carrying their tiny magnetic moment, add up to a measurable field. In a piece of magnetized iron, vast numbers of atoms have their spins pointing in the same direction, and the cumulative effect is the familiar pull of a magnet. The compass needle that has guided sailors and explorers for centuries works because of the spin quantum number and the exclusion principle that forces electrons into their particular arrangements. Copper, with one more electron than iron, has a single electron sitting alone in its outer s orbital while its d subshell is completely filled. This lone mobile electron gives copper its extraordinary electrical conductivity. The electron moves freely through the material, carrying charge with it, which is why copper wire is how we move electricity from one place to another. The building fills, floor by floor, room by room, seat by seat. Each element is defined by where its last electron sits and how many empty rooms remain nearby. The entire diversity of matter, every metal, every crystal, every gas, every compound that can be formed, is encoded in this filling order, this patient accumulation of electrons into their quantum addresses, each one uniquely its own, none of them sharing the same 4 numbers. The periodic table is, in the end, a map of quantum real estate, and the rule that governs it, the rule that says no 2 electrons can share the same address, is the reason the map has the structure it does. Vienna, in the last years of the 19th century, was a city of extraordinary intellectual energy. The old empire was still vast, still glittering at its edges, and the city itself was alive with music and philosophy and science and argument. It was into this world that Wolfgang Ernst Pauli was born in April of 1900, the son of a distinguished chemist and the godson of Ernst Mach, one of the most influential philosophers of science of the era. The name Wolfgang Ernst was chosen in Mach's honor. The choice of godfather was not accidental. Pauli's father moved in the highest intellectual circles, and he wanted his son to grow up breathing the same air. He did. By the time Pauli was a teenager, he was reading Einstein's papers on general relativity, not popularizations, not summaries, but the actual papers, and understanding them. When he arrived at the University of Munich at 18 to study under Arnold Sommerfeld, he was already, in some respects, ahead of the curriculum. Sommerfeld, who recognized talent with the ease of long practice, was frank about it. He later said that Pauli had been fully formed as a physicist from the beginning, and that his own role had been less to teach than to provide a direction for what was already there. Pauli's review of general relativity, written when he was 20, ran to over 250 pages and was so comprehensive and so clear that Einstein himself praised it, not with the mild approval one gives to a promising student, with genuine admiration. But alongside the brilliance, there was the severity. Pauli was constitutionally unable to pretend that a wrong idea was anything other than wrong. He had, as one colleague described it, an almost physical discomfort in the presence of imprecision. If you presented a theory to Pauli and the theory had a flaw, he would find the flaw and he would tell you about it directly, without softening. His letters to colleagues are full of passages that begin, "I must tell you frankly that," and then proceed to dismantle whatever was sent to him. His most famous phrase was, "not even wrong." It was his verdict on arguments that were so poorly constructed they couldn't be evaluated at all. Not right, not wrong, but formless, incoherent, not yet science. It sounds harsh. But in the world Pauli inhabited, where a single poorly reasoned argument could send a field chasing shadows for years, the service of rigorous criticism was real and important. He was, as his colleagues eventually agreed, the conscience of physics. The Pauli effect was something else. It was a joke. but a joke with enough repeated coincidences to take on a life of its own. The story was that experimental equipment malfunctioned in Pauli's presence. Glassware broke. Instruments gave nonsensical readings. Experiments failed inexplicably. Since Pauli was a theorist who rarely set foot in a laboratory, the effect was conveniently difficult to disprove. Otto Stern, the experimental physicist, reportedly banned Pauli from his laboratory entirely, not entirely in jest. There was a famous incident at the University of Göttingen, where a complicated apparatus broke down without obvious cause on a particular afternoon, and it was later established, or at least claimed with great amusement, that Pauli's train had passed through Göttingen at exactly that moment, en route to somewhere else. He never even got off. Pauli himself found the legend entertaining. He had a sense of humor that was dry and precise, like his science, and he was capable of genuine warmth toward people he respected. His friendships with Niels Bohr and Werner Heisenberg were among the most intellectually productive relationships in the history of physics. He and Bohr would argue for hours with great energy and mutual respect, neither one willing to give ground until the argument had been resolved by something resembling actual physics. Heisenberg, who was almost exactly Pauli's age and had been a fellow student under Sommerfeld, was perhaps his closest intellectual companion. Their letters, stretching over decades, are among the great documents of 20th century science. In 1930, Pauli did something that, by his own standards, was almost reckless. He proposed the existence of a particle that had never been observed, that had no charge, that had almost no mass, and that interacted with other matter so weakly that it could pass through the entire Earth without being stopped. He proposed it to explain a puzzle in radioactive decay, a process in which a nucleus emits an electron, and in which the energy of the emitted electron was observed to vary continuously rather than taking a fixed value. Energy conservation, one of the bedrock principles of physics, seemed to be violated. Either energy conservation was wrong, or something was carrying away the missing energy undetected. Pauli chose to save energy conservation. He wrote a letter, famously addressed to "Dear radioactive ladies and gentlemen," since it was sent to a conference he couldn't attend, proposing the existence of what he called, in German, a neutron, though the name would later be changed to neutrino, meaning little neutral one, to distinguish it from the much heavier neutron discovered by Chadwick in 1932. The neutrino, Pauli wrote, was a desperate remedy. He was not happy about proposing a particle that might never be detectable. He said he had done a terrible thing, proposed a particle that could not be seen. He also famously bet a case of champagne that no one would ever detect it. The bet stood for 26 years. The neutrino was so weakly interacting, so ghostly, that building a detector capable of catching one seemed almost impossible. But in 1956, Frederick Rains and Clyde Cowan, working with a nuclear reactor in South Carolina as a source of enormous numbers of neutrinos, managed to detect them. The signal was unmistakable. The neutrino was real. Pauli received a telegram with the news. He was 56 years old, and he had been carrying the bet for more than a quarter of his life. His telegram in reply read, "Thanks for message. Everything comes to him who knows how to wait." Pauli. It is a perfect sentence, warm, wry, entirely characteristic. The patience he claimed he had shown was, of course, mostly the patience of the experimenters who had spent years building the detector. But the grace of the reply, the lightness of it, the way it holds the years of waiting without complaint, says something real about the man beneath the severity. He received the Nobel Prize in Physics in 1945 for the exclusion principle. The prize was awarded in absentia. He was in Princeton, having fled Europe during the war, and the ceremony in Stockholm went ahead without him. He gave his Nobel lecture the following year, and it is, like everything he wrote, precise and clear and entirely free of false modesty or unnecessary flourish. He died in 1958 in Zurich in a hospital room that happened to be numbered 107. The number 137 had haunted him for decades. It is the approximate value of a fundamental constant of nature, a pure number with no units, called the fine structure constant, that describes the strength of the electromagnetic force and appears throughout atomic physics. Pauli had long been fascinated by it, had called it one of the greatest mysteries of physics, had wondered aloud why it should have the value it does rather than any other. Finding himself in room 137 at the end of his life, he noted the coincidence. Whether he found it meaningful or merely characteristic of the universe's fondness for irony is not recorded. What is recorded is the work, the exclusion principle, the neutrino, decades of letters and papers and arguments that kept physics honest, that refused to let a wrong idea slide unchallenged, that demanded the kind of rigor without which the whole enterprise becomes something softer and less useful than it should be. The conscience of physics. It is a title that was given to him with affection, and it fits. Everything we have explored so far has taken place at the scale of the atom. Electrons moving in their quantum addresses, shells filling in sequence, chemistry emerging from the arrangement of the outermost occupants. It is a story of the very small. But the exclusion principle does not stop at the boundary of the atom, or the molecule, or the material. It operates across the entire universe at every scale, including the most enormous scales imaginable. To see this, we need to follow a star to the end of its life. A star like our Sun is, at its core, a site of continuous nuclear fusion, the process by which hydrogen nuclei are pressed together under enormous pressure and temperature until they merge, forming helium and releasing energy. This energy, flowing outward through the star's body, creates a pressure that pushes against gravity. The star is held in a balance, gravity pulling inward, the pressure from nuclear fusion pushing outward. For billions of years, these two forces are matched, and the star maintains its size and its warmth. But fusion requires fuel, and eventually, the fuel runs out. When a star like our Sun exhausts the hydrogen in its core, the fusion slows and then stops. Gravity, no longer opposed, begins to win. The core contracts. The contraction heats the surrounding layers, briefly igniting a shell of hydrogen fusion that causes the outer layers to expand enormously. But this is a last flourish. Eventually, the outer layers drift away into space, forming a beautiful expanding shell of glowing gas called a planetary nebula, and what remains behind is the core, a dense, hot remnant roughly the size of Earth, containing a mass comparable to our Sun. This remnant is a white dwarf. A white dwarf contains an extraordinary amount of mass in a very small volume. A teaspoon of white dwarf material would weigh several tons, not because the atoms are different, but because they are packed together far more tightly than in ordinary matter. In ordinary material, atoms are mostly empty space. In a white dwarf, that space has been squeezed away. The electrons and nuclei are compressed until the electrons are packed together as tightly as the exclusion principle allows. And here is where the exclusion principle becomes a structural force of cosmic importance. Those electrons, crammed together, cannot all occupy the same quantum state. As they are compressed, the lower energy states fill up, and the electrons are forced into higher and higher energy states. Higher energy means higher momentum, and higher momentum means the electrons are moving faster. Faster moving electrons push outward against the compression. This outward push, this pressure generated not by heat or by any ordinary thermal motion, but purely by the quantum refusal of electrons to share states, is called electron degeneracy pressure. It is the pressure that holds a white dwarf up. The word degeneracy here is a technical term from physics, meaning that multiple quantum states have the same energy, or that particles are being forced into the lowest available states in a highly compressed system. It does not mean broken or degraded. It means the electrons are in their minimum possible configuration, as fully packed as the exclusion principle allows, and they are pushing back. Electron degeneracy pressure has a remarkable property that distinguishes it from ordinary gas pressure. Ordinary gas pressure depends on temperature. Heat a gas and its pressure rises. Cool it and the pressure falls. Degeneracy pressure does not depend on temperature in the same way. A white dwarf can cool over billions of years, losing its heat to space, and the degeneracy pressure that holds it up remains essentially unchanged. The star does not collapse as it cools. It simply becomes a cold, dark, inert object, a black dwarf, though the universe is not yet old enough for any white dwarf to have cooled that far. The scale of what degeneracy pressure is holding up is worth sitting with. Our Sun has a diameter of about 1.5 million kilometers. A white dwarf formed from a star like our Sun has a diameter of roughly 13,000 kilometers, comparable to Earth, the same mass, compressed into a volume about 1 million times smaller. And what keeps it from collapsing further is the electrons' quantum insistence on their own individual states. But electron degeneracy pressure has a limit. If a white dwarf accumulates additional mass, perhaps by drawing material from a companion star in a binary system, there comes a threshold beyond which the electrons can no longer hold back gravity. This limit was worked out in 1930 by a young Indian physicist named Subramanian Chandrasekhar, who did the calculation on a ship voyage from India to England. The limit, physicists call it the Chandrasekhar limit, is about 1.5 times the mass of our Sun. Beyond that mass, electron degeneracy pressure is insufficient. The collapse continues. What happens next depends on the mass of the collapsing core. For cores near the Chandrasekhar limit, the collapse is catastrophic. The electrons are forced to combine with protons, converting them into neutrons, and the entire core transforms in a fraction of a second into a ball of neutrons roughly 10 to 15 kilometers across. This is a neutron star. A neutron star is almost beyond imagination in its density. A teaspoon of neutron star material would weigh not tons but hundreds of millions of tons. The entire mass of a star, more than our Sun, compressed into a sphere smaller than a city. And what holds a neutron star up is the same principle that held the white dwarf up, applied now to neutrons rather than electrons. Neutrons are also fermions. They also have half-integer spin. They also obey the exclusion principle, each one requiring its own unique quantum address. The outward pressure generated by this quantum refusal, neutron degeneracy pressure, is what prevents the neutron star from collapsing further. In 2016, physicists detected gravitational waves, ripples in the fabric of space itself, produced by two neutron stars spiraling together and merging. The signal, detected by instruments so sensitive they could measure a distortion in space smaller than 1,000th the width of a proton, lasted less than 2 minutes. In those 2 minutes, the merger released more energy than our Sun will produce in its entire 10 billion year lifetime, and the objects that produced it were held together, right up to the moment of collision, by the exclusion principle acting on neutrons. If even neutron degeneracy pressure is overcome, which happens in the most massive stellar cores, the collapse continues without limit, and the result is a black hole where gravity has won completely and no known force, quantum or otherwise, can halt the compression. But for most stellar remnants, the exclusion principle is sufficient. The white dwarfs and neutron stars scattered through the galaxy are monuments to a quantum rule discovered in a laboratory in the 1920s, scaled up to cosmic dimensions, holding the remnants of dead stars in a quiet, permanent quantum equilibrium. The universe is full of them. Billions of white dwarfs in our galaxy alone, each one supported by the same principle that fills the periodic table. Each one a testament to the fact that the exclusion principle is not merely a rule of chemistry, but a structural feature of the cosmos. There is a particular kind of scientific commitment that goes beyond simply using a law. It is the commitment to testing it, to asking with the best instruments available whether the law might have an edge, a boundary, a condition under which it softens or fails. This is not doubt. It is the deepest form of respect for a rule, to probe it carefully and persistently at the very limit of what can be measured. The exclusion principle has been tested in this way, and the story of how it has been tested is one of the quieter, more patient stories in contemporary physics. Deep beneath the mountains of central Italy, in a tunnel drilled through the rock of the Gran Sasso Massif at a depth of about 1,400 meters, there is a laboratory. The mountain above it provides a shield against cosmic rays, high-energy particles from space that rain down on the surface of the Earth constantly, and that would overwhelm the signals of sensitive detectors if those detectors were not buried. Down in the rock, the background noise of the cosmos is reduced to almost nothing, and experiments that require extraordinary quiet can listen for extraordinarily faint signals. One of the experiments running in that underground quiet is called VIP2. The name stands for Violation of the Pauli Exclusion Principle, and the experiment does exactly what the name suggests. It searches for violations. The logic of the experiment is elegant. The exclusion principle says that in a copper atom, the inner shells are full. The first shell holds 2 electrons, both of them with their quantum addresses completely occupied. No additional electron can join them. If you bring a fresh electron into the copper and it somehow, against the exclusion principle, slipped into that already full first shell, it would need to release energy as it settled in, and the energy it would release would be emitted as an X-ray photon, a particle of high-energy light with a very specific wavelength. A wavelength that would not be produced by any normal process in copper, because normally no electron can make that transition. The X-ray would be a signature, a fingerprint of a forbidden event. What VIP2 does is run a current of electrons through a copper strip. Fresh electrons, electrons that have never been part of a copper atom before, are flowing through the material. If any of them were to violate the exclusion principle and squeeze into a full inner shell, the experiment's detectors, exquisitely sensitive devices called silicon drift detectors, capable of measuring the energy of individual X-ray photons with great precision, would record the signal. The experiment has been running with various upgrades for years, and it has found nothing, no signal, no forbidden X-rays. The exclusion principle holds. But the value of the experiment is not simply the absence of a signal, it is the precision with which that absence can be stated. The VIP2 experiment has established an upper limit on the probability of a violation, the maximum probability that any given electron could violate the exclusion principle, consistent with the data. That upper limit is approximately 3.4 times 10 to the power of negative 29. Written out as a decimal, it would require 28 zeros after the decimal point before any other digit appeared. This is an almost incomprehensibly small number. To give it some scale, if you imagined performing 100 million trillion trials, each one an electron passing through copper and having the chance to violate the principle, you would expect, on average, to see fewer than 4 violations. The exclusion principle, as far as VIP2 can determine, is not merely approximately true, it is true to a precision that strains the imagination. Why bother searching at all for a violation so small it would be almost impossible to detect even if it existed? The answer is that the exclusion principle is so fundamental, so deeply embedded in the structure of quantum mechanics, that any violation, however small, would be telling us something profound about the nature of reality. Phi. It would mean that the framework of quantum mechanics, the most precisely tested theory in the history of science, was not quite complete. It would be a crack in the foundation, and cracks in foundations are worth finding. There is also a theoretical motivation, some speculative extensions of quantum mechanics, theories that attempt to connect quantum mechanics with gravity or that propose new structures at very small scales of distance suggest that the exclusion principle might not be absolutely exact. It might hold to extraordinary precision but fail at some level that current experiments cannot yet reach. The VIP experiments are exploring that possibility, pushing the measurement further with each iteration. The next iteration is VIP3. A 2024 paper described the new detector array being prepared at Gran Sasso. The upgrade involves thicker silicon drift detectors, capable of capturing X-rays with greater efficiency, and extends the search to heavier elements beyond copper. Zirconium, silver, palladium, tin, elements with more protons, denser electron clouds, higher energy X-rays that would be produced by any violation. The heavier the element, the more energetic the forbidden X-ray, and in some respects the cleaner the signal. VIP3 aims to push the upper limit on violations down by at least another order of magnitude, to find nothing, but to find it more precisely than before. There is something deeply characteristic about this kind of science. It is patient in a way that most human endeavors are not. The experiment runs for years. The data accumulates slowly. The answer, when it comes, is almost certainly going to be the same as the answer before. No violation detected. And that absence, that continued, reinforced, deepened absence is the result. The result is the silence. It is also worth noting what happened in 2016 in a rather different kind of experiment that gave a vivid, direct demonstration of the principle. Physicists working with ultra-cold clouds of fermionic potassium atoms, atoms cooled to within a fraction of a degree of absolute zero, so cold that quantum effects dominate their behavior, collided two such clouds together and watched how the atoms scattered. When identical fermions collide, the exclusion principle creates a forbidden zone. Two indistinguishable fermions cannot scatter off each other at a 90-degree angle to the direction of the collision. This is a direct consequence of the antisymmetry of the wave function, and the experiment confirmed it. The 90-degree scattering was suppressed, exactly as the theory predicted, by the exclusion principle acting on identical atoms. It is a beautiful thing to see. A rule this abstract produce, a visible gap in a scattering pattern, a hole in the data where the principle says nothing can be. The mathematics and the measurement agreed, and the agreement was clean. The underground laboratory continues its patient work. The silicon drift detectors listen in the quiet beneath the mountain. The electrons flow through the copper strip, and the exclusion principle, so far, has not flinched. There is a thought that Paul Ehrenfest put into words in 1931, and it is one of those thoughts that, once encountered, is difficult to let go of entirely. Ehrenfest was a physicist of great insight, a colleague and friend of Einstein and Bohr, someone who had spent his career thinking carefully about the foundations of things. In 1931, he noted, quietly in a paper that was more meditation than announcement, that the stability and volume of ordinary matter depended entirely on the exclusion principle. Without it, he said, all the electrons in every atom would collapse into the lowest possible energy state. Every atom would shrink to a point. Every piece of matter in the universe would implode into a dimensionless, structureless, undifferentiated nothing. Not compressed, not dense, nothing, no size, no shape, no chemistry, no materials, no world. The chair or bed you are lying on has the hardness and the volume it does because the electrons in its atoms refuse to share quantum states with each other. When you press your hand against a surface, the electrons in your hand and the electrons in the surface push back, not because of any direct force between them, but because occupying the same region of space would require them to share quantum addresses, and that is something they cannot do. The solidity of the world is a quantum effect. The resistance you feel when you touch anything at all is the exclusion principle, asserting itself at the boundary between your atoms and the atoms of whatever you are touching. This is true of every solid surface in the world, every wall, every floor, every stone and tree and bone. The structural integrity of matter, its refusal to simply pass through itself, is not a consequence of some special bonding force between atoms. It is a consequence of the exclusion principle, which makes atoms occupy volume in the first place, and which makes that volume resistant to compression. Think for a moment about the air in the room where you are resting. Each breath you draw contains hundreds of billions of molecules: nitrogen, oxygen, a little carbon dioxide, and water vapor. Each molecule is made of atoms. Each atom has a nucleus surrounded by electrons in their shells. Those electrons are distributed through a volume that is, by the standards of the nucleus, vast. The nucleus of an atom is roughly 100,000 times smaller than the electron cloud surrounding it. And yet atoms do not pass through each other, because the electron clouds, governed by the exclusion principle, do not overlap freely. The oxygen you are breathing right now is carrying the exclusion principle into your blood with every breath. The hemoglobin in your red blood cells, large, intricate protein molecules built around iron atoms, carries oxygen from your lungs to your tissues. The iron atom at the center of each hemoglobin molecule holds oxygen in a particular way, releasing it at precisely the right pressure, because of the specific arrangement of iron's electrons in their d subshell orbitals. Those 5 rooms, partly filled, their spins arranged in a pattern that gives iron its particular chemical character and its magnetic properties. The oxygen is loaded and unloaded through a sequence of quantum state changes, each one governed by the same rules we have been tracing all evening. The carbon in every protein in your body, in the enzymes that catalyze your metabolism, in the collagen that gives your skin its elasticity, in the keratin of your hair and nails, is carbon because of its 4 outer electrons and their particular orbital geometry, which we traced earlier through the 2nd floor of the quantum theatre. The nitrogen in your DNA, the phosphorus in the backbone of each strand, the hydrogen bonds that hold the 2 strands of the double helix together. Each of these is a consequence of electron configuration, and electron configuration is a consequence of the exclusion principle filling the available states in a particular order. You are, in a very literal sense, the shape you are because of this rule. The molecules that make up your cells, the cells that make up your tissues, the tissues that make up your body, all of it assembled from the chemistry of electrons in their quantum addresses, none of them sharing, each one uniquely itself, each one holding its place in the structure. And the structure holds through the night. Right now, as you rest, the electrons in every atom of your body are doing exactly what they have always done. They are sitting in their shells, in their subshells, in their orientations with their spins. The carbon atoms in your bones are the same carbon atoms that were forged in the cores of stars that died billions of years before the Earth existed. Those stars burned their hydrogen to helium, their helium to carbon and oxygen, and at the end of their lives they scattered those elements into space. The carbon drifted through interstellar gas clouds for hundreds of millions of years before finding its way into the chemistry of a young planet, and eventually into the chemistry of life, and eventually into you. And through all of that, through the interior of dying stars, through the cold of interstellar space, through the slow chemistry of early oceans, through every cell that has ever been part of a living thing, there is something very still in that thought. The rule is not enforced from outside. There is no mechanism checking that electrons aren't sharing states, no policeman of the quantum world. The rule is simply true in the same way that mathematics is true, not because anything makes it so, but because the alternative is self-contradictory, a wave function that must simultaneously change sign and stay the same, collapsing to zero, erasing the configuration from the space of possible things. The universe, at its deepest level, has a kind of order that is not imposed but intrinsic. It is not order that has to be maintained. It is order that cannot be otherwise. And within that order, you are here. Breathing slowly, the electrons in your lungs cycling through their states as oxygen is absorbed and carbon dioxide released. The neurons in your brain, each one a cell, each cell made of molecules, each molecule made of atoms, each atom held in shape by the exclusion principle, are quieting now. The activity of the waking day is fading. The patterns of your thoughts are becoming slower, softer, less defined. The iron in your blood is moving through your body with each heartbeat, each iron atom holding its oxygen cargo in that precisely configured d-orbital arrangement, releasing it where it is needed, accepting more at the lungs, cycling through the night without rest, without error, guided by quantum rules that have never changed and will never change. Somewhere above you, the stars are carrying their own version of this story. White dwarfs held up by electron degeneracy pressure, cooling slowly over billions of years, their electrons packed into the lowest available states, the exclusion principle keeping them from collapse. Neutron stars spinning in the dark, their neutrons pressed together as tightly as the principle allows, sending pulses of radio waves across the galaxy with a regularity that makes the best atomic clocks look imprecise. And out in the spaces between galaxies, the same quantum rules, the same 4 quantum numbers, the same antisymmetric wave functions, the same absolute prohibition on shared states. The rule that Pauli found in the data of spectral lines in 1925, the rule that he followed from anomaly to principle, that he named without fully understanding its physical meaning, that Dirac later showed to be a mathematical inevitability, reaches from the electron clouds of a hydrogen atom to the surfaces of neutron stars. It reaches from the chemistry of carbon to the structure of the periodic table. It reaches from the solidity of the ground beneath you to the stability of the remnants of dead stars. It reaches, in the end, to here, to this room, to you lying still in the dark. The electrons are holding their places. The atoms are keeping their shapes. The molecules are maintaining their structures. The cells are doing their quiet work. Everything is held, gently and absolutely, by the same rule that has held it through all the long history of the universe. The day behind you is already distant. The questions that felt urgent this morning have grown soft and far away. The world outside is doing what it always does, continuing, patient, governed by its deep and unhurried rules, and you have no need to attend to any of it right now. The exclusion principle is holding everything together. It has been doing so since the first atoms formed, and it will continue to do so long after tonight has passed. Drift now, if you are ready. Eat well.